Hello, dear students. Today we are going to perform experiment number E02. The name of the experiment is Prove the Kirchhoff's Law, and in this experiment our aim is to design a simple circuit uh, with low power supply and different resistors, and then we will prove Kirchhoff's laws in that circuit. And as you know, the Kirchhoff's current law says the algebraic sum of currents in a network of conductors meeting at a point is zero, that is sum of I equal to zero. And from the Kirchhoff's voltage law, we know that the directed sum of the potential difference around any closed loop is zero. That means sum of voltage is zero. So to perform the experiment, we will require a couple of apparatus. First one is analog trainer board, and here we can see from our arrangement that this is the analog trainer board. Here is three different resistors. This is 100 ohm, this is 47 ohm, this is 100 ohm, and we have two DC power supply, and we have connecting jumpers. These are connecting jumpers, and we have multimeter for the measurement. So as we explained Kirchhoff's current law and Kirchhoff's voltage law in brief, so we have designed a very simple circuit which is shown here. So here you can see that a resistor is connected with a voltage source, and here is another resistors, and here is another voltage source, and here is another resistors is connected. And to connect with the Kirchhoff's current law, actually we can say that the current entering in this node, and also this current is entering in this node, and this current is leaving in this node, leaving from this node. Okay, so I1 is entering, I3 is entering, and I2 is leaving. So we will see from table 1 that the sum of this current is 0. That means I1 plus I3 minus I2 equal to 0. So let's explain a bit about our circuit arrangement in this trainer board. Here you can see that a potential is applied in this loop from this voltage source. This is basically a DC supply, and from this voltage source we have also applied for this loop. Okay, so in this trainer board, the basic idea is this 9 points are actually connected, but these 9 points are disconnected with these 9 points. That means this block is separated from this block. Okay, so that means within this with using this jumper cable, okay, so jumper connector, we are basically connecting this block and this block. So you see that we have completed the path by putting this jumper connector. The other thing is the multimeter. The multimeter is currently at DC voltage. You know that this is V, and the straight line means that DC voltage. So to measure the DC voltage, this knob should be here in this range, and whenever we want to use the current, then we have to settle this in this area. Okay, and the multimeter actually operated in voltage measurement when we put this cable here. Okay, so yeah, so you see that this is milliampere. That means this is actually used, this port is used when we measure the current. So that means this should be here. Okay, so to measure the DC current, and to measure the DC voltage, we should place this positive terminal here, and this knob should be in this range to measure the DC voltage. So let's see a bit more about the DC power supply. Here is our DC power supply, and you can see that you are able to choose different range. For example, right now it's 0 volt because this regulator is at the 0 position. That means this is 0 volt, and whenever you turn placed here number 1, that means 3 volt, and then 6 volt, 2 corresponds to 6 volt, then 3 corresponds to 9 volt, and 4 corresponds to 12 volt. So we are using two different voltage sources, and we will maintain actually two different voltage here. Okay, so here I will show you how the circuit is arranged in the trainer board. We will be using this jumper cable to connect these two blocks, and next we put 100 ohm resistor as designed, and we are completing the loop from here. Okay, so the first loop is formed using another resistor 47 ohm, and yeah, here is another jumper connector. So let's put another resistor here. This is 100 ohm as written here in this figure. And now we are connecting the DC power supply. So this DC power supply is applying potential difference across this loop. Okay, and another DC power supply is applied. You know that this loop is still not completed, but right now this is completed. That means we have made the connection here. So this voltage source, that means this voltage will be applied in this loop. So right now we would like to show you from the circuit diagram that how current is flowing in this tree loop. Okay, in this different area. So here you can see that I1 is flowing in this direction, I3 is flowing in this direction, and I2 should be the sum of I1 and I3. So that means I1 is entering in this node, I3 is entering in this node, and I2 is leaving from this node. Okay, so from this arrangement we have already placed these two power supplies, and from where 6 volt is coming from here in this loop, and 9 volt is coming in this loop. Okay, so for this voltage or applied EMF, we are going to measure the current. In the first loop we can measure using the multimeter. So yeah, so as from the convention of current, you know, the current will be flowing in this direction. So from here you can see that 0.02 ampere, 0.02 ampere, okay, is flowing in loop 1. Okay, so we are noting down the value 0.02 ampere for the loop 1. And now we were interested in measuring the current I3. So that's why we are disconnecting this jumper connector, and also from the convention we know that current should be flowing in this direction, so from negative to positive direction. Okay, so we found that this is 0.05 ampere, and we are also noting down for current 2, which is I2, 0.05 ampere. Okay, and now we are going to measure this current I2 and sorry, there is a correction. We have measured actually I3 in this loop, and which is 0.05 ampere, 0.05 ampere. Can you show the measurement again, please? Yeah. So in this area, this is 0.05 ampere in this loop. Okay. So now we are interested in measuring I2. So which should be the current leaving from this node, okay, in this direction. So as I told you that current should be leaving from this node in this direction. Okay, so we saw the current is measured 0.07 ampere, 0.07 ampere. So we're noting down current I2 is 0.07 ampere, 0.07 ampere. So now our task is to clarify that from the Kirchhoff's current law that I1 and I2 will summed up and should be subtracted to I2, and which will give 0 ampere. So that means we can check it. 0.02 plus 0.05 minus 0.07, and this should be equal 0. So this is 0 ampere. So the sum of the total current in this diagram according to the KCL gives 0 ampere, and which proves the KCL law. And similarly, we can do some more measurement using two different types of voltage. For example, from here we can select right now 12 volt from here and 9 volt from here. So that here we set 9 volt and here it is 12 volt. Okay, so we can continue our measurement. So now we have applied 9 volt in this loop and 12 volt for this loop, and for a different measurement we will continue. So first we will measure I1, and you can clearly see the meter reading from here. And so you can see that from I1 in this loop it gives 0.04 ampere, okay, from the multimeter reading. So we are noting down as like we did before. For I1 this is 0.04 ampere, and for I3 this is I3 which is entering through this node. So I3 gives 0.07 ampere. So I3 gives 0.07 ampere. And now we are going to measure I2. So I2 should be equal to the sum of I1 and I3. So you can clearly see that 0.11 ampere, and which is the sum of I1 and I3. So we're noting down 0.11 ampere. So it steals the same clarification that the current entering in this node, that means this current and this current entering in this node should be summed up, and which is equal to the current leaving from this node, which is I2. Okay, So we can check the calculation, and this is 0.07 plus 0.04 ampere minus 0.11, which gives 0. So we can see the result from here. So once again, we applied 6 volt here, and we applied 12 volt here for the second loop. Okay, so from the measurement you can see the current, which is roughly 1 ampere through the loop 1. So 0.01 ampere, sorry, 0.01 ampere. And for the loop 2, we can see that the current I3 is around 0.08 ampere. And now we are going to measure I2, and you have to check whether Kirchhoff's current law is proved here. So the current I2 is 0.09 ampere. Okay, so now you you should verify whether this measurement proves the Kirchhoff's current law. So now we will be checking Kirchhoff's voltage law, and for that we will consider 3 different loops. So the first loop is this one, the second loop is this one, and the third loop is this one. So for the first loop, according to Kirchhoff's voltage law, the applied EMF V2 should be equal to the voltage drop across R1 and R2. And we will do this measurement at first. So we applied here 6 volt for the first loop, and we will check 6 volt which is V2, right? And we will check the voltage drop across this resistor. So the applied EMF is roughly 6.30 volt, and the voltage drop across R1, which is 100 ohm, is so the voltage drop in this resistor R1 is 4.36 volt. So that means I1 R1 is 4.36 volt. 4.36 volt, and next we will measure I2 R2. So we see that I2 R2 is 1.93 volt. So we are noting down this value, 1.93 volt. So you will check using the Kirchhoff's voltage law how it is acting at the loop 1. And next we will do the measurement for loop 2. So one other information is, while we were measuring voltage drop across loop 1, we kept it to 0 volt. Okay, and we kept here 6 volt. That means 6 volt is applied only for this loop. And right now we are going to measure in loop 2, so that's why we should keep it in 0 volt, and we will apply here 12 volt. So again, for loop 2, you can see that V1 is applied, and the voltage will be dropped across 100 ohm and 47 ohm. So we will be measuring for loop 2 V1, I2 R2 and I3 R3. So let's measure What is V1? So V1 is 12.34 12.34 volt. And how much is I2 R2? Which is in opposite direction. Change the direction. Which is 4.07 volt. So I2 R2, that means the voltage drop across this resistor is 4.07 volt. And now we would like to measure the voltage across R3, which is 8.24 volt. So you will also check the Kirchhoff's voltage law for loop 2 according to the measurement. And now we will measure the voltage for loop 3. So for loop 3, you can see that, and this is the whole loop. And now we will consider these two voltage source and these two resistors, and these resistors will be also here. And we will follow this equation, V2 minus V1 plus I3 R3 minus I1 R1. So for this, we will need to measure V1, V2, I1 R1, and I3 R3. So from this equation, we have to first measure V2. So let's measure V2. And of course, we have applied 6 volt here and 12 volt here. That means 6 volt is applied in the loop 1 and 12 volt is applied for the loop 2 simultaneously. And right now we will measure V2. So V2 is 6.35. V2 is 6.35. So this is V2. And V1 is 12.35 volt. And now we will measure I1 R1. So now we are measuring the voltage drop across the resistor R1, which is 1.75 volt. 1.75 volt. And now we are interested in measuring I3 R3 across this 100 ohm resistor. Reverse the direction. Which is 7.73. 7.73 volt. So here our measurement is completed, and we will check this measurement here. So the value from here. Okay, so for loop 1 we see these values, and for loop 2 we see these values, and for loop 3 we see these values. Okay, so using Kirchhoff's current law and Kirchhoff's voltage law, we have done this experiment to verify these two statements. So there is some important information. Usually when we measure the voltage across a resistor, we connect the digital multimeter in parallel with the resistor, because the voltage drop in voltmeter, the resistance is high, and for the high resistance actually no current flows, and across the resistor the high voltage is dropped, so we can see the voltage in this multimeter. And in case of measuring current, we Usually, according to our convention, we follow this series measurement. That means we connected this probe with here, and in series we connected this probe. So that means the resistor, internal resistance, actually very low, and the current flow through the resistors, and the uh, the current can be shown here, shown from here. Yeah, so it's like 0.02 ampere. So that's the information around for regarding this experiment. Thank you.